some examples here. Incidentally, at this point, let me point out that if you don't feel well with double integrals and writing iterated forms in double integrals, it would be difficult for you to understand triples. So doubles are the key here. So you should be very comfortable with double integrals, writing iterated forms, using polars, and other things. Okay. Triples are just direct but quite insignificant generalization at this point. Well, express double integral over S in iterated integrals. Okay. In the first case, let S be the sphere, okay, x squared plus y squared plus z squared is our sphere. So it is something like this. Where the radiuses are. Well, firstly, is it a simple region with respect to x, y, or z? The answer is quite obvious. It is, of course. Actually, it is simple with respect to all three of them. So let us take z first. Now, this is, okay, call this S, is simple with respect to z first. Okay. Also with respect to x or y. Okay. How? Well, you have an upper and a lower surface, as we already had. Okay. You have some surface at the top, and you have a surface at the bottom. The sides are vertical. You exactly have this situation. These are the upper and lower hemispheres. Okay. But actually, okay, the curves here, okay, coincide. So actually, the two surfaces are glued together. Okay. So, I mean, they are squeezed, so you don't see this vertical part, but it is still a simple region with respect to z first. So, a triple integral over S would be a double integral over, well, the lower one is, of course, z is the negative of r squared minus x squared minus y squared. And the other one is the positive of r squared minus x squared minus y squared. So it changed from minus root r squared minus x squared minus y squared up to the positive one. And then you integrate with respect to other variables over d. What is d? Well, d is what you see when you look from the top. It's the projection. So d is a circle with radius r. Okay, in the xy plane. So let me write it completely. This is Okay, z changed from minus root r squared minus x squared minus y squared up to r squared minus x squared minus y squared, one negative root, the other the positive root. Now, after that, you have many choices. For example, this is a region with respect to y first, so we can put here dy, dz. Then y will change from minus r squared minus x squared up to r squared minus x squared. In the meantime, x will change from minus r up to r. So this is the Cartesian version directly. Okay. Where in the second stage we used y first. You could, of course, change the places. Or one can use 4D. Well, S is a region in space, so polars are not yet meaningful for it. Okay, so we can write this as remember, this was the negative root of r squared x squared y squared, and this was the positive root. Now, changing the rest, this is the integral over d now. If we change it into polars, of course, we have the Jacobian coming, and r will change from 0 to r. We are in a circle of radius r, theta 0 to 2 pi. Well, of course, there is something strange here. The strange thing is that this is the function we are integrating in the polar conversion. So here, okay, xy's must be changed into r theta. Okay, so let us do it. 0 to 2 pi, 0 to r. Now, if we change the inside values to r's and thetas, of course, this will be minus root r squared minus lowercase r squared minus r squared at the top, f of r cosine theta, r sine theta, z is z, we did not change that, dz, r dr, d theta. Of course, you can put this r if you want to the front over here, but not outside the integrals yet. You can put it outside the first one, but not the others. Okay, so this is the polar used in the version of the iterated integrals. You have choices here. Okay. Well, the second example is S is bounded by Z is 1 minus x squared minus y squared, and the coordinate planes in the first octet. Well, this is actually probably the first time we are using the word octant, first octant. It signifies the following. In plane, okay, we divide the plane into 4 pieces, into 4 quadrants. In the first quadrant, we have x and y positive or 0. Well, when you do the same thing to the space, okay, the coordinate planes divide the space into 8 parts. Okay, first octant means that x, y, z are all non-negative. Okay, so the coordinate planes now bound the figure, and the figure is clearly an upside down paraboloid. So we get the following picture. Okay. Well, when x and y are zeros, z is 1, and minus makes an upside down paraboloid. 1 says you shift it up, so it becomes a paraboloid of this form. We are not interested with the rest. We're interested only in what happens in the xy system. Of course, what happens in the xy system is something like this. In the first octet. This is 1, and this surface is the upside down paraboloid. It is bounded by the coordinate planes, so it's bounded below by z equal to 0, at the back by x equal to 0, at the front with y equal to 0. It's in the first octant, so this is the region of integration. Now, of course, this is a simple region. If you look in the z direction first, you enter from z equal to 0, you leave from the paraboloid. But the same is true also for x or y first. So this is a nice simple region with respect to all coordinates chosen first. So in particular, okay, S is simple with respect to Z first. Okay. So integral over S of F would be F Z, Z changing from 0 up to the upper part, and then you integrate over D. Okay. Now, what is D? Of course, D is what you see when you look from the top. Well, if you look from the top, what you see is a quarter of a circle, okay, with radius 1. Because there, okay, what you see is the base, z is 0, so x squared plus y squared is 1. So it follows that our integral can be written as, okay, I will not use Cartesian here, just use, say, polars. Because we have a circular piece, so polars are easier to use in the double integral. And of course, I have here 0 to 1 minus, well, x squared plus y squared is r squared. I have r cosine theta, r sine theta, and z, and r and dz, of course, r dr theta. In this quarter circle, r changed from 0 to 1, but theta not 0 to 2 pi, but only up to pi over 2. Okay. So this writes S, integral over S, as a nice iterated integral. Okay. As a third example, let S be given by a paraboloid and a plane. 2x plus 1. Now, this of course says that you have a paraboloid and you cut it, okay, by a plane. So necessarily, okay, if you want to get a region, a bounded region, this must be above the paraboloid, and it is. Okay. Actually, in defining S. So what does S look like? S is, okay, a paraboloid like this, a standard paraboloid, and Z is 2x plus 1, does not have any y in it, okay? So it moves along y. So if you sketch this in the zx plane here, it will be a straight line, and you move it, okay, along y. So somehow you are cutting this with a plane of this form. Okay? It doesn't, of course, pass through the y-axis, something like this. So you cut it with a plane of that form. So clearly what you get will be something as follows. You will have, okay, a paraboloid, but at the top, this is cut by a plane. So this is units. Well then, of course, it is simple with respect to Z first. Okay. Well, we usually take Z first because it's simpler and easier to visualize. But it doesn't have any specialty other than that. Because it's simple with respect to Z first, an integral over S of F in triples would be, okay, an integral over D of, now in the Z direction, you enter from the paraboloid, leave from the plane. So you start from x squared plus y squared up to 2x plus 1, f of x, y, z, dz, and dA. Now to complete the job, we need to find out what D is. Well, D is the projection of this onto the xy plane. So it will be something like this. Okay. So D is determined, it's the inside part, by the curve, okay, of intersection of the paraboloid and the plane. So, okay, we have x squared plus y squared equal to z, and that is 2x plus 1, which of course says that we get x minus 1 squared, y squared, what happens? Equal to 2. Okay. So then, okay, so our D happens to be, okay, a circle whose center is at 1, 0, and whose radius is square root of 2. Well, square root of 2 is bigger than 1, so it's something like this. Okay. The radius is square root 2. So this is 1 plus root 2, and this is root 2 minus 1. Okay. Oh, sorry. 1 minus root. It must be a negative number. Okay, so this is our d. Now, let us write our iterated integral over d. Well, so our integral would be as follows. Now, when we look at d, we see that in either way, it is a simple region with respect to x first or y first. So let me take y first. Okay. Actually, d is simple with respect to both x or y first. Okay. But say we take y. Well, y change, firstly, z changes from the paraboloid up to the plane. And now y changed from the lower circle up to the upper one. Well, the upper lower, of course, means that you solve for y, and y would be square root of 2 minus x minus 1 squared. Okay. But at the bottom, you have the negative of it. At the top, you have the positive of it. Okay. In the meantime, x changed from 1 minus root 2 up to 1 plus root 2. So this is a standard way of writing it. Okay. Well, you can, of course, choose to use, in this case, a polar transformation, because this is a circle after all, so circles are good for polars, but this is not a standard circle. Its center is not at 0, 0. So you can perhaps choose to use, when evaluating the double integral part, to shift it first, that is, make a modified polar transformation. What does that mean? Well, x is r cosine theta normally, but you want to add 1 to it so that center is at 0. Or better, subtract, I mean, one of them. And then you figure out what to do. The Jacobian does not change. It's still r, because it doesn't affect the derivative. However, inside f, you have to write the new values. Okay. So let me just comment. One can use here, okay, modified polars. Namely, x is r cosine theta, y is r sine theta. These are standard polars. But we modify it, okay, so that when we subtract 1 from x, we just get r cosine theta, so we add 1. So x minus 1 now is r cosine theta, so the sum of the squares is r squared. Okay. And so the circle then becomes okay, put x minus 1 squared plus y squared. Well, that becomes just r squared equal to 2. So r is square root 2. It is as simple as you can get it. Of course, you have to find out the Jacobian, but it's still r, so nothing changes in there. Okay. Okay, now let us find the volume of a cone. Okay, a cone in the standard way. That is an elementary geometric cone. So it is something like this. So with inside, so it is not the infinitely long cone that we consider in quadratic surfaces. It's not a surface in the first place. It's a solid. Let me call this S. So the volume wanted is obviously triple integral over S of 1. Now this is the volume of a cone if S is the cone itself. Okay, now how do we formulate this? Well, indeed, it is a standard form. It's a simple form with respect to Z first. If I put my origin here, okay, so put that here, say xy. Then, of course, okay, in this form, S is simple with respect to Z first. Okay. So the volume, let me call it V0. V0 will be then integral over D, okay, of the cone up to the upper surface. Upper surface is clear. It has a height h. So it's the horizontal plane z equal to h. Okay. So here z changes from the cone up to h. 1 dz. And then we evaluate over dA. Okay. Now, what is the cone equation here? Okay. The cone equation, remember, is something, okay, where you have direct proportions and so on. So, to find the equation of the cone, okay, let us look at what we see here. Okay. This is h and this is r. Okay. For any small r, okay, we always have, okay, what do we have here? For any small r, the ratio, of course, is the same. So r over h is r over h. And the angle that we have here, that is, say, phi, it is, well, r over h is the tangent of phi. Okay. Which means, of course, that r, sorry, this is h. So r is h times tangent phi. But, okay, well, what do we know about that? If we call this Z actually, then R over Z is the same. Okay? So we have this relation between Z and R all the time. Here R is the distance from the Z axis, so it's the polar R. Okay. So this tangent phi is, of course, R over H. So we have Z is H over R, which happens to be square root of x squared plus y squared times H. Okay. Well, here we considered the upper part of the cone. So if you want to consider the infinitely long cone, okay, you should square them. So Z squared would be H over R, x squared plus y squared. Now here, what is a little bit new for us is the following. We know that the cone equation was Z squared is equal to x squared plus y squared. But that was a cone where the angle here was 45 degrees. But here it's not 45 degrees. It's arctangent of H over R. Okay? R over H. Okay. So this factor H over R comes into the picture because in our cone, the angle with the z-axis is not pi over 4. So we had to calculate that. Now we know the equation, and so the rest is easy to calculate after this. Hence, V0 will be, okay, 1 dz. Now from cone to H, well, the cone is H over R, square root of x squared plus y squared. Okay. And then we have dA over d. Well, when you look from the top, d is a circle with radius r. So d here is a circle with radius r. So we use polars, standard polars. Then this becomes r dr d theta, r from 0 to r, theta 0 to 2 pi. Now what happens to the inside part? The inside part is 1 dz. Well, the top was h, of course, from the geometry directly. So it starts from h over r, but this is just the polar r up to h. Okay. So this clearly gives us h minus h over r, okay, multiplied by r. Then you have h times r, so it is h r squared over 2 minus h over r. You have r squared here, so r cubed over 3. I'm integrating this one from 0 to r. And then I will integrate 0 to 2 pi d theta, but there's no theta here. So it's just 2 pi. Okay. And if I put r, I get h over 2 minus h r square in both cases. So that would be h r square, 1/2 minus 1/3, 2 pi, and that would be 1 over 6. So that would be h r squared pi over 3 as expected. It's the volume of a cone. Okay. Of course, we have many ways of calculating this, but this is just one of them. Let's continue with the following example now. Let us find the volume of the solid bounded by the surfaces x squared plus y squared is a squared, and x is a, y is a, z is 0, and z is x plus 1. Here, of course, a is a positive number. Okay. Now, the trouble here is certainly not the rather simple surfaces given, but that sketching the figure, there are too many of them. We should not be confused, because the only ones which involve z are the last two. Okay. Let us forget that for a minute. These three conditions are, because there are no z's in them, they go vertical up in the z direction. Along the z direction, we remember that from the original sketches we had. If there's a missing variable, then the surface is just going in that direction in the constant way. So it's vertical in the z direction here. So let us forget the z direction, just sketch them in the xy system. Obviously, this is a circle of radius a. So because it's radius a, x is a is here, and y is a is here. Now, when we look at all these pieces, we see actually two pieces bounded by them. One is bounded by the circle alone. Okay. The other is here. As I remarked earlier, if nothing is specified, we take the one which is determined by all of them, which necessarily points out to this region. So this is our D. Okay. Now, what happens to the whole thing? Well, if you move this vertically up, clearly you get the following. Okay. So this is our D now. If you move it vertically up and down, you get something like a triangular shape going up and down. Now, these are the sides in question. Okay. If we consider all three curves, this is what you get. We are, of course, dealing with the inside part. Now, this is cut by z is 0, so this plane, and somewhere by some other plane. I'm not sketching them accurately, but it's some other plane. Well, on top of z is 0 and on top of this triangular shape, okay, x plus y is always positive. So this plane is higher than this one. This is positive on top of B. In other words, this is bigger than this. So this is the upper surface, this is the lower surface. And when we look from the top, of course, this D is what we see. So the volume, which is the triple integral of 1 over S, will be, because S is simple with respect to Z, okay, starts from 0 at the bottom, goes up to x plus y, 1 dz, and then you integrate over dA. Okay. So this is then integral of x plus y dz. And now looking at D, well, you can use anything you want, but firstly, you have horizontal and vertical lines. In polars, it's not very good, as we already had an example before. Even though you have a circle, you probably would not like to use polars here. You can, if you want, okay? I will write it in y first version. It's simple with respect to both x and y anyway. So I will put here dy first and then dx. And y changed from the circle up to a. Circle is a squared minus x squared up to a. And x changed from 0 to a. So this is the integral in question. Well, you can calculate it like this, or if you want, you can use polars. But in polars, it's advisable to take theta first, because it's simple with respect to theta first, not r. With respect to r, okay, your r starts from the circle but hits either x equal to a or y equal to a. So you have to divide, as we did before. We had such an example before, so I will not go into the calculation of that. Okay. My sixth example is to find the volume of this solid bounded by the following curves. X squared plus y squared is ax. X squared plus y squared is a z. And z is 0. Of course, throughout, a is a positive number. Okay. Now, to make a sketch of what's happening, okay, first of all, the middle one is a almost standard paraboloid. Z is x squared plus y squared with a factor, but it's a positive factor, so it does not change the shape too much. Okay, and z is 0, it's obvious. So let us see what this is. This, of course, okay, is a circle with radius, with center at x minus a over 2, so at a over 2. Okay. And clearly, radius is likewise a over 2. So this is a. In other words, if y is 0, x is a or 0, and you get this immediately. So the radius is a over 2. So this is our d in question. Actually, it's not our d, but it is what this says. Okay. It's a circle with center shifted a little bit, but radius is a over 2. Now, the other one is a paraboloid on top of this. Well, let us try to sketch it. Okay, here we have a circle that is along the x direction, so it's like this. Okay, with a here and a over 2 here, etc. And on top of it, we have a paraboloid. Okay, and we have the xy plane. Okay. Now, firstly, this is not a circle because we are in 3 space. It is a cylinder. Okay. It's a cylinder which goes up and down. And somewhere the paraboloid cuts it, and somewhere z equal to 0 cuts it. Well, so visualizing, we see that actually the whole figure is somewhere here. It's on top of the small circle. At the top, you have the paraboloid. Of course, the circle lies in the xy plane because that is 0. So that determines the figure. So the figure is perhaps something like the following. You have this at the bottom, and you go vertical up, but until you hit the paraboloid, which gives you something like this. Okay, this is carved because this is the lower part of the paraboloid. The sides are vertical. Okay, so this is our S in question. So what we know from here is that the upper surface is this one and the lower surface is 0, and D, of course, is this one. So then, the volume in question would be triple integral of 1 because we have a simple region with respect to, okay, Z first. So it is 1 dz, sorry, I mean, of course, 1 dz, and dA, and Z changes from 0 up to the paraboloid. Okay. Now A, okay, being a circular region, but shifted, okay? You may want to use polars if you want, so perhaps we should, okay, use polars directly. Okay. That tells us that we have x squared plus y squared over A, that's integral with respect to Z, r dr d theta, all right, and r changed from, in this d here, okay, from 0, it moves in all directions, and always it hits the circle. So we have to find what this circle is in the polar language. So, okay, r starts from 0, hits the circle. In the meantime, theta, okay, starts from here, from 0, but goes up to here, because this is tangent, but then you're off. A better idea is to start theta from negative pi over 2 and go up to positive pi over 2. Okay, so I will do that way. Okay. Now the circle is x squared plus y squared is ax, okay? So it is r squared is ar cosine theta, so r is a cosine theta. So this becomes minus pi over 2 up to pi over 2, 0 to the circle a cosine theta. This is r squared over a times r dr d theta. Now you can easily calculate that. That would be r cubed, so r to the 4th over 4. So that's the, right, that's the 4th power of cosine theta. Well, that integral is a little bit more difficult than I anticipated. Yes, it is a little bit. So one has to work over that. Yeah, fine. And of course, you get from here, okay, 1 over a, and the 4th power of cosine over 4. And at 0, you have 0, so d theta minus pi over 2 to pi over 2. Okay. Well, I will not finish this calculation. It's a good exercise in what? In integration techniques. Now, okay. Now, perhaps a better idea is the following. Instead of using polars directly here, we can use modified polars. Okay, what does that mean? X is our cosine theta, and y is our sine theta, but we modify it so that the circle sits at the origin. Its center sits at the origin. Well, how do we manage that? Well, its center is shifted by a over 2, so we add a over 2 here. Okay. Then, circle becomes, okay, x minus a over 2 squared plus y squared, that is the circle, actually. It's the shifted one here. Is a squared over 4, namely, let me do that, x minus a over 2 squared plus y squared is a squared over 4. Now, this is nothing but r squared in our new formulation. So, r is a over 2. Now, the Jacobian, well, in the Jacobian, since we take derivatives of r's and thetas, this a over 2 does not count. And the Jacobian is still r. Since we take derivatives only, we did that for the usual polars. This a over 2 does not make any difference. So the whole thing then is the following. From minus pi over 2 up to, let me calculate that. We have the double integral of x squared plus y squared over a. R is still the same, dr d theta. But now, okay, the new d is a circle centered at the origin with radius a over 2 because of this here. It shifted our circle to the center. Well, for this d then, here we get 0 to a over 2 for r and 0 to 2 pi for theta. Okay. Well, but x squared plus y squared is not r squared anymore. We have to be careful there. This is 0 to 2 pi, 0 to a over 2, okay, 1 over a. Now, x squared plus y squared, if you look at here, okay, is a little bit different. It is then, let me rewrite it completely, r cosine theta plus a over 2 squared plus r squared sine squared theta, that's y squared, okay, r dr d theta. Now, in this square, we have r squared cosine squared, that makes r squared. Cosine squared plus sine squared is 1. We have a squared over 4 here. And then we have twice, okay, a r over 2 cosine theta. Now what do? We integrate. Firstly, r here changes between constants. So when we integrate, we can integrate with respect to theta first if we want. And integral of this would be sine theta. Okay, r is a constant, but 0 to 2 pi, it gives 0. So this term, 0 to 2 pi, gives 0. So we don't have that term. So the whole thing is 0 to 2 pi, 0 to a over 2, okay, 1 over a, r squared, plus a squared over 4, times r, the r dθ. And, okay, this is easy now. That is, because we have no theta, we have 2 pi coming. We have 1 over a constant. And then we will integrate the r part. It would be r cubed over 3, r to the 4th over 4, plus a squared over 4r, so r squared over 2 comes 0 to a over 2. Okay. So this is 2 pi over a times, now if we put a over 2, we are taking a over 2 to the 4th power out, plus divided by, okay, this out, so we have 1 over 4 coming here. We have a over 2 squared here, another a over 2 squared, so it's again the same power. So we just have 1 over 2 here. So it becomes 2 pi over a to the 4th over 16 times 6 over 8. Okay. Simplification tells us what? We have 4 here. We have, say, 3 here. So it is 3 pi a cubed divided by 32. Okay. So this was the volume.